Welcome. This is the LLM Makerspace series. It's primarily a code-driven series. Today we're going to talk about TikTok scale personalized recommendations. So 1 million writes per second on a recommender style system. And normally we do only code in these series, but I'm going to do a little bit of background information because personalized recommendations at scale requires a little bit of background knowledge. So I'm going to do a little bit about that. So I'm talking about doing 1 million writes per second. We can see this is Hopsworks here, and you can see I have a table of interactions. This is what we call a feature group. This is interaction data, and you can see it's writing in around 1 million writes per second. We can see that there. And this has been going on for quite some time. I actually started this yesterday. This is a Flink application that's written 6.272 terabytes of data in that time. So, and yeah, we won't skip at that. So that's basically the scale part. I'll get into the scale later, but what I'm going to do is I'm going to start by talking just a bit about the problem of personalized recommendations and the TikTok use case. I'll show you the code then for building a personalized recommendation system. It's available on the GitHub repo. You'll get all the links later on. And then we'll look at the scale. We'll look at some of the benchmarks, the setup that I have here that's taking in 1 million writes per second, and we're actually running about 100,000 concurrent reads from the system in parallel. So both reading and writing to the platform. And we'll explain why that scale is necessary for some classes of applications. So let's kick it off, and I'm going to talk a bit about, first of all, about TikTok, and then apologize for the slides for those of you who came here for the code. We'll get into the code later, and please ask questions in the chat, particularly if you want something clarified. TikTok is a really good recommender system, and I think more than anything else, if you see the second underlying comment here, it reacts very quickly, extremely quickly to changes in your behavior. So this ranker and recommendation system is often called digital crack. I've seen that by not just Andrej Karpathy, but other people going at that. And the basic architecture of these scalable personalized recommendation systems, and they're used at all hyperscale AI companies, is what we call the retrieval and ranking architecture. So in TikTok, we have hundreds of millions or billions of videos, and they're all indexed. They're indexed for approximate nearest neighbor search. So that's a vector index. And when you want to search for something, or when you click on something, or when you take any form of action, the system will give you recommendations of videos to look at next. And to do that, there's a couple of stages that it goes through. Firstly, using the user's history and context, there'll be a number of candidates generated. Now, that number typically is in the order of hundreds. And those hundreds of candidates, we want to rank or personalize them based on your history, the context, so what's trending and so on, but also properties of the videos themselves. So as we call features in machine learning. And ultimately, what you will get back as a user of the platform is this ordered ranked list of recommendations. And you may click on one or the other. And what you really want here is this fast feedback loop. When you take an action, we would like the recommendation system to take into account the action you've taken as fast as possible. And that leads to, obviously, sustainable competitive advantage. And then the process of when you take a click or an action to getting a recommendation, typically you'll have an end-to-end latency in the order of 50 to 100 or 200 milliseconds. And there's we can see a lot of infrastructure required to generate hundreds of candidates, rank all of those, retrieve it. We're going to have to retrieve a lot of information about those candidates as well before we rank them, and then presenting them to the user. So there's quite a lot of, we call this a fan-out architecture. All right. So what do TikTok themselves say about it? Well, they've written a paper, and they published it called Monolith. It's a relatively okay paper. I would say it's not a great paper. The reason why it's not a great paper is it only covers one particular aspect of TikTok. That aspect is what we call real-time training, which is not a very common thing you see. But it does talk about the architecture, and in particular, they talk about how they collect all of the actions, all of the clicks, and log them to Kafka. And then they have a Flink job, which is at this scale of millions of concurrent actions arriving per second, it's generating features. Now, many people think that when I click on TikTok and I take any form of action and it reacts quickly to that action, that what has happened is that that action that I took, which ended up in Kafka and the Flink job updated, became a training example. We trained a new model. The new model became available for serving, and that's how the platform learned. In fact, that's not how the fastest feedback loop. So this training, this asynchronous online training is a process that happens on a schedule. So it's not going to happen every 10 seconds, every minute. It's going to happen over a longer period of time. But what does happen at the interval or scale of a couple of seconds is that the actions you take will be updated as features. They'll be generated as what we call small pieces of information, the features, the inputs to your model. So for example, I clicked on a video of type entertainment or sports. Well, that click will be registered in here. The category of the most recent video I clicked on will be sports. And that will be used as input to the model. So the model will use the fact that, oh, I see you just looked at sports to recommend things related to that. So that's the form of this very fast feedback loop. So we look at the scale part, we're going to look at Kafka Flink, and we'll look a little bit about how we optimize some of the types of feature engineering jobs we do in Flink, particularly windowed aggregations. But we'll look at the whole architecture as a whole, how we build one of these personalized recommendation systems at scale. Okay, so a little bit of reminder that TikTok, even though it's a very good recommender, is not necessarily a great platform for society. So be very careful if you're going to build one of these, that you don't do what TikTok has done and led to a lot of people, particularly people who are vulnerable, following recommendations down paths they don't want to go down. We have a question here from Seong J. Wang. He asks, what does the parameter synchro part do? So this is from the paper, the TikTok paper, the Monmouth paper. So this parameter synchronization. So what's happening in the paper describes actually an online learning system. So the Flink jobs here generate training examples, and they have historical training examples on their large HDFS cluster. And what happens is these training workers will pick up these new samples. They'll basically create some, effectively, because they're training, many workers are training the model in parallel. So what we have is the single shared state for the model is here, but each model has a replica of the model locally. So I believe they're doing data parallel training, not necessarily model parallel, but I may be incorrect. I don't remember the details in the paper. But basically, each worker will take a bunch of samples as they arrive here. They'll pass them through the model. They'll compute the gradients. The gradients will be sent to this parameter training server, which stores all the parameters for the model. And then periodically, as the model's weights are updated, they get synchronized with a model that's actually used to serve client or user requests. Now, the frequency at which that happens is not at the second level. I'm not familiar exactly how frequent it happens, but it's at the order of minutes in any case. So you're basically you're retraining your model, you're updating the weights continually, and then you're synchronizing those changes with the model that's being served. Now, in many cases, I've seen this happen in the past, and it's very dangerous because, users can attack the system with, I remember some of the first systems that came out to do voice recognition in Sweden. People started saying terrible things to it. And then the model started learning those terrible, I think, racist things, and it became racist very quickly. So that's something to be careful about. Okay. Right. So let's move on from there. So let's have a look at the code. I'll just jump into the repo because I've talked a little bit about the problem, and this is our repo here. So this is the repo here. It's under my colleague David's his username. We haven't merged it to our official Hopsworks repo, but it will be at some point in the near future. You can see this code in here in Python and in Java. So the scalable part where we're writing 1 million of these click stream events per second is a Java program in Flink. You'll find it in here. You can see in here we have a pipeline, which is our TikTok stream aggregation pipeline. I assume most people here are not necessarily Java programmers, so I won't go through the details of the Flink code. I'll talk a little bit about the abstractions in Flink and performance considerations later on. But the Python code here, we're going to go through today. So this Python code here are a number of notebooks we can see. And primarily what we're doing is we're taking historical data to create tables of features that we're going to use to train our model with. We're not going to have just one model. We're going to have a retrieval model, or we're going to have a ranking model and an embedding model, a couple of embedding models actually. And then we're going to create models as deployments. And there's also some work with vector databases in here, hence the LLM part of the platform. So we'll get into that in a little bit. Okay. This is the repo. It is public. I do believe it's public. There's a question on that just there. Okay, so the code is structured as follows. So the way we're structuring this system and the way we see many scalable machine learning systems or AI systems structured is that you'll have feature pipelines that take raw data, in this case, the clickstream events, and they'll output the features and also labels if you have outcomes as well. And those features are used as input to a training pipeline, and the training pipeline will output a trained model. And then you'll have an inference pipeline. In this case, we're looking at online inference. We're going to have user requests come in, and the model will make a prediction. And the user requests that come in will not just use the user information, maybe the click that you took, or maybe the swipe that you took. That's a very information light action. So getting just a click or getting a swipe, there's not much information content in it. So we're going to go to a feature store to enrich that, to get all of the history of what you've done recently and what other people have done, to build a more rich feature vector, which will help us then make better predictions. In this case, ranking of the recommendations. So this is how it's kind of put together. You'll see that you'll have a feature pipeline, training pipeline, inference pipeline, and they connect via this shared state layer at the bottom. They don't, this R in the middle is a logical R. They don't talk to each other. They basically write to the shared layer, read from the shared layer, and write to the shared layer. And that shared layer consists of, Hopsworks has a feature store, and the feature store has two main abstractions. We have the tables of features called feature groups, and then we have the selection of features used by models called feature views. So feature views are just metadata. The actual data is stored in feature groups. And recently we added support for vector indexes. So you can say this column in the table or feature group is actually embedding. You compute the embedding and then you insert it into the table, and then it becomes available for similarity search or approximate nearest neighbor search. You're able to basically find the rows that have values similar to the value that you entered in, the rows in the table. There's also a model registry in Hopsworks, and we'll see also that there is model serving. So Hopsworks supports Kserve, which is the de facto Kubernetes open source model serving framework. This is basically what we're going to work with, and this is what we'll use to scale to 1 million operations. Just to remind you that the data is written to feature groups, but we read from these feature views. So you can have streaming pipelines like Flink. When we have historical data, we'll have batch pipelines. And many instances, we have customers who would like to keep the offline data in their own data warehouse or data lake. In that case, we just have external tables. So the data is not stored in Hopsworks, it's just mapped in there. And then the feature views are the API for getting the real-time data, so low latency lookup of pre-computed features, but also we have these high throughput data frame style APIs for getting batches of data for training models, but also for inference. Right. I'm going to just explain a little bit of background on how we build a personalized recommendation system at scale with the retrieval and ranking architecture, and in particular the two-tower model, which is a little bit counterintuitive. And I think I need to explain it in order to look at the code in a minute. So what we need to do to get started is we need to actually collect interactions between the users and the videos they're watching. So when a user takes an action on the app, when they search for something, when they swipe, when they navigate, those actions are connected to a set of recommendations. So in TikTok, you'll see that, you know, when you're watching a video, you'll see recommended videos beneath it. These are the videos 1 to 4 that we're showing here. Now, the user will take an action based on the recommendations that have been displayed, and that interaction we need to store. So for example, if we have video 2 here and the user clicked on video 2, but then swiped away very quickly, we'll give it a score of 1. So the duration maybe was low. But video 3, the user spent a longer duration, we'll give it a score of 5. And the other videos 1 and 4, the user didn't click on, but that's also a signal. If the user didn't click on it, we also should capture that. So we can see that as you're taking actions, and we have millions of concurrent users on TikTok, every one of them, every time they click or swipe or so on, we get a user video interaction that we need to save, because that's going to be the training data for the architecture, what's called a 2-tower embedding model and ranking model that we're going to train in a minute. So what's slightly counterintuitive, if you may have heard of embeddings, and you may know that, for example, if I take an image and I compute an embedding for the image, and I take lots of images and store them in a vector index, I can find similar images when I present an image, and that's great. I have one image to find other images, so we're using the same modality. I'm using a new image to find similar images. But in this case, we want to do something different. We want to have the user's history in TikTok, and then we have the database of videos, and we want to say, okay, the user had this history. This is what's popular and trending at the moment. What should I recommend? There are two different modalities. So can a user query find videos with similarity search? It's a very counterintuitive idea. And the way it works is, yes, the answer is you can, but we have to have this grounding in the click stream we have here. When the user has their history, they clicked on this video, but they didn't click on this video. This is the data that grounds the two modalities, brings them together. It brings together the user's queries, but also the videos that they clicked on. So the way we're going to do it is we're going to have one embedding space for the user queries and one for the videos. And those two will be the same dimensionality. So both our embedding space will be the same, and we're going to train them together with what's called a 2-tower model. So let's have a look at how it works. This is the basic theory. This is a Google animation here. It's quite nice. You can see here that we're putting in books. We're putting in Shakespeare books, Romeo and Juliet, Great Expectations, King Lear, Pride and Prejudice, that's Jane Austen. And now we want to search for something, Shakespeare tragedy. So we expect it to end up close to the Shakespeare books. They're the nearest neighbors, not close to Pride and Prejudice, Jane Austen. So how is this working? Well, it's working basically because we're building up an index of our books, and then we have a user query which is going to find the closest books in the embedding space. So the embedding space in our case with TikTok will just be the videos, and then the query tower will be the user's actions. So what they searched for, or maybe the last video they clicked on, or the swipe they did. So we're going to map it into the same embedding space where the videos are. So we're only going to store the videos in the embedding space. The user queries will be used to find videos in the embedding space. So we're going to store all of this user video interactions training data. Now, I did show you earlier, well, how much data could that be? I've been running 1 million operations per second since yesterday sometime, and I've collected 6.8 terabytes of data. Now, these video interactions are not huge. If we have a look at the data we have in here, we can see we have the video category, the interaction date, the ID of the interaction, the month, the type, the user ID, and the watch time. So there's not a huge amount of data in every row. It's on the order of 50 to 100 bytes, I believe. But if I'm writing 1 million operations per second, we can see quite a lot of data gets accumulated over time. So let's go back here to the slides. So we're going to have a lot of this training data here, and we're going to use it because we're training an embedding model. We'll need GPUs, and we will train both of the user query embedding model, is the encoder part, and then the video embedding model, the encoder part, with the same training data. So the user's preferences, their history, what they clicked on. So at the moment the user clicked on the video, so at this point in here, when the user clicked on the video, we'll have a history of what are the 5 most recent videos the user has looked at, what is the most popular category of video they like, what's the most recent category of video they've liked, and so on, what's trending. All that information are features for the user input here. So they're going to go in here. And then we'll have information about the video. So how popular is the video? How many people have viewed it within a recent period of time? How many people have liked it within a recent period of time? So we're going to have a lot of information about the videos, which we're going to have to compute as features. So we'll look a little bit at how we use timed windows and windowed aggregations to compute those at scale. So these features are going to be stored here. We'll have the raw clickstream data. It's going to compute the features, and then with the features, we're going to train the models. What it's basically going to do is feed in a sample. So a sample would be one of these rows here, where we said, here was the user, this is the video they clicked on, and this was the score. So this is the score is what we're trying to optimize here. This will be our in this case, it'll be our label or our target. As we pass in a training sample, we'll get a score, which will be 0 for non-interaction. And I gave you the number 5 as the highest interaction, but it could be a 1. Let's make it a 5 to be consistent. And then if the sample said it was actually a 5, but you had a 0, then the weights will be updated in both the user query and video encoder towers to reflect that loss was quite high. But then, of course, if the prediction was close, if the predicted loss was close to the actual loss on the click, then the weights would not be updated as much. You're getting closer to what you hope to have. So once we have these two, when this training is finished, we'll have two embedding models, the user query embedding model and the video encoder model. We can do what we saw earlier with the Shakespeare books. We can take all of the videos and we can insert them into our vector index. So you can have in this case, a Spark job would probably be a good way to do it. Take all of your videos, compute the embeddings for all of them, and insert them into your feature groups. So let's have a look at what that would look like in Hopsworks. We would have our videos here, and we can see that there might be some activity on this before. I'm not sure how many rows I wrote. It wasn't that many, 25,000. This is a smaller one, I should add. This is not the scalable one I'm running. And we can see here that there's a bunch of parameters related to the video. So there also is the candidate embeddings feature group. So we can see here that we also can have embeddings. And if we insert an embedding into our feature group, then for this particular feature group, we can do then the similarity search for this particular one. Okay. So we're going to insert it into a feature group. That feature group will have a column that's an embedding column, and then we'll be able to do similarity search on it later. So this is what you'll find in the GitHub repo. This is the data model for our retrieval and ranking architecture. Every click you make will be written to the interactions table. And we can see here that this is very much raw data. We'll have watch time, the type of interaction, whether it's a click or a swipe or whatever, the time at which it happened, the user who clicked on it, and the video they clicked on. And from that, we can compute features. Now, we don't have very complicated features in here. We just have the number of views, the category of the video, the number of likes, and so on. We can compute embeddings from the videos as well, and then we have user information as well. But we can see here that the user actions, the swipes that are happening, they're gonna end up in Kafka, which is a scalable event bus. I'll show you the architecture in a minute, but I'm running 3 virtual machines with 16 CPUs, and that's handling over 1 million concurrent writes. And then I have a streaming pipeline, in this case, a Flink application, which is taking those 1 million events that happen per second, and it's writing them to this feature group in Hopsworks. This is an online feature group that we're able to query in less than a couple of milliseconds. So from there, we can compute more features. And in the Python example, we have the feature pipelines to compute the other features from our interaction data, but also from the user data and from the videos themselves. So it's a pretty straightforward data model. Somebody asks the question, what is an embedding? So I gave an example of embedding earlier. So an embedding is, at a high level, an embedding is we take some complex information, so high-dimensional information. So high-dimensional information for the user embedding would be, well, what's the user's, maybe their age, maybe we take their geography, the history of what they've clicked on for the last day and week. And we can take a lot more information about the user, and we can even take information about what's trending. If I was to store all of that information, I may have a very large amount of information that's difficult to work with. What an embedding can do is compress that into a number of floating point numbers. And that number is the dimensionality of your embedding. And it could be 512 bytes. It could be 512 floating point numbers, sorry, which would be 4 bytes each, or it could be 1024 or 2000. But when I have that embedding, I can put them in a vector index, and then I can find similar embeddings, and they maintain the same semantic meaning. So if those embeddings were images, and I inserted an image and said, here's a new image, it would show you the closest images. And if I did the same for text, it would show me the closest text. So that's what the embedding is there for. It's going to do the retrieval part of our personalized recommender. It's going to basically find, in this case, what are the candidate videos that we think are closest to the history of what you've been searching for. Okay, great. So the architecture as a whole, while we'll have many different tables, some of them will be updated at different cadences. So maybe a user will update their profile periodically. We won't need to have that updated in real time. The set of videos will arrive, maybe people are uploading videos the whole time, but it'll be batch jobs that schedule them to be indexed, and they won't run necessarily in real time, but can be run on a schedule, maybe every 15 minutes or every hour. They'll then update these tables. So let's start by looking at, because we're looking at scale as well here, we're going to look at this streaming feature pipeline and how we can do streaming feature pipelines at massive TikTok scale. This is the setup I have. We have 6 Flink workers with 56 CPUs each. That's a total of 336 CPUs and quite a lot of memory. This is running on GCP. I can just show you briefly this. I think I have it on GCP engine here. This is it. So I have basically, these last 3 are for the readers. So I have a benchmark running these three readers. And then we have these 6 nodes are running Flink. And then we have 3 nodes running Kafka. We have a number of connectors running here, and then we have 4 database nodes, and then the Hopsworks head node. And I can show you that better here on the slides. But this is basically the setup. So we have readers or Locust. Locust is a client benchmark that we can run. And Flink are the writers. So the actual infrastructure in Hopsworks are these nodes in blue. There's a total of 168 CPUs. And the data that's written from Flink is written at about 0.5 GB per second. And from there, it's about 400 to 500 megabytes per second, or 0.5 GB again, to some connectors. And those connectors ensure that we get a stable flow of data into the online store. And we look at the latency end to end of that. It's quite low, and I can show it to you here. If we go to our, this is the test, we go to the online metrics. So this is the Flink job is writing to this table here. And these online metrics basically show us how many, we can see here we've got 1 million writes per second roughly in the last 20 minutes. We can go back to other timescales. We can see here that the connector has to take the event from Kafka, deserialize it, process it, and write it to the online feature store. And we can see here that the P99 latency is in the order of 40 milliseconds. So it's very low. And even if you go to a hard, timescale here to an hour or 5 hours, we'll see that those numbers are very stable. So the end-to-end time from the Flink application writing the data to ending up in the online feature store is, on the order of less than a second or so. If we think about overall architecture and tiers, how many tiers are in this architecture from Boris? Thank you, Boris. Let's have a look. So the architecture effectively has our, these workers here are effectively simulating the TikTok clients, the handsets. So this is not part of your infrastructure. Typically, the way this would work at somewhere like TikTok is they would have points of presence or endpoints, and those will collect the clicks, and those clicks will then get sent to Kafka. So this is our first layer. Our first layer is where the data arrives in our platform, and from there, that data gets written into our online feature store, RonDB, via a connector. So it's really only 2 layers. We have a writer here writing the data in, and then we have the intermediate layer to ensure, and the reason why we have Kafka here is for high availability. So every layer of this architecture is scale out. So when a client writes to Kafka, it has high availability. There's quorum-based replication. We know that the data will be there even if one of the brokers fails. We also have the next layer is also replicated and highly available. This is typically would run on Kubernetes. You'd scale up and down the number of these connectors as you need them. They're stateless. And what they do is they basically do work stealing to take the data from the Kafka topics and write them to the online feature store. And then the online feature store, in our case, is our database that we developed called RonDB. It's a fork of MySQL cluster. And here I'm running 4 data nodes, but we can scale it to, I think the maximum is 256 nodes, but in practice, people tend to stay below 100 nodes. So we can scale that up with an order of magnitude or more as needed. The other part of the architecture is Hopsworks itself as a REST API. The vector index is currently running here, so we're not actually benchmarking the vector index. We can scale this out as well. So we could have multiple versions of Hopsworks here. We could to scale out the vector index, but what we're also evaluating in the benchmark is the read performance. And the read is actually being spread over a number of MySQL servers, which I've deployed on these different VMs. So we have some MySQL servers on the 4 RonDB nodes, the 5 connector nodes, and the 1 head node running Hopsworks. And those MySQL servers make calls then on the backend database. So everything here is obviously secure, authenticated, authorized with access control. And we can see here that the performance number for the writes is about 1 second end to end. And for the reads, we can have a look in a second. We looked at this already on the web page, but this is the number for the reads. I'll just zoom in to show you. I think I have it on the web page as well. I'm running 21,000 concurrent clients on the 3 VMs with 56 CPUs each. It's using Docker Compose. It's running the Locust benchmark, which is a well-known benchmark client. It's running 76 containers using Docker Compose, and each container has 100 users. So you can see this is the number of users being scaled up. And let's look at it on the web page. I think it's a bit clearer. This is the web page here as one of them. I have a few of them here. But what we can see happening here is that, let's look at this one. We have the number of requests per second. So as the number of users increases, we get to the kind of stable state here. We have 96 users, and we can see we're getting around close to 38,000 concurrent reads per second. So these are all primary key lookups. They're all reading individual rows from the online feature store. And we can see that the response time is 1 millisecond for the 50th percentile, but it increases to about 4 to 5 milliseconds for the 95th percentile. So that's basically how we are benchmarking. I'll show a little bit about the code now, just to get it out of the way. We have this GitHub repo called Feature Store API, and in here the Locust benchmark is there's instructions for how to run it. So if you want to run this on any Hopsworks cluster, you can. It'll create one table, and it'll read from that table. So you run this code to create the table, and then you run Locust. And I'm running it with distributed Locust with Docker Compose, because you need lots of concurrent clients to be able to read at that scale. Okay. So what's about the runtime and cost per hour? So FinOps on GCP. So the question is about how much is this going to cost you? So the infrastructure part here is currently 168 CPUs, okay? And it's kind of, at this stage, we've, if we look at the load, if you're curious, I'll just jump. Sorry, there are people who are interested in this. I'm going to show you. This is the Grafana and Hopsworks. We have Grafana for lots of things. We can have a quick look. There's Kafka there. Let's move this thing out of the way. It's in my way. So we can see, like, even if I go over the last, I think we've about 10, it's extremely stable, so you can barely see the difference. But if we look at the load on the virtual machines, this is running at the moment. We'll be able to see the Kafka one, I believe, is, let's have a look. It's this one here. We can see this is CPU utilization. So you can see it's about green is user or idle. So about 40% idle on that host there. We pick some other ones at random. You can see it's 25% idle. So there is enough overhead to do more jobs. This one has 60% idle CPU. There's not memory pressure here, but we do have a lot of network I/O on these. So the virtual machines themselves, I think they're written in the slides here. The types you can see there and look them up yourself. The total cost, I think, I'm not sure off the top of my head, but you'd need to work it out. But it's significant. But I think if you run it on GCP, it would be more expensive than running it on Heartsnur. Hopsworks you can deploy anywhere. So if you really care about cost, the cloud is quite expensive, and you can run this on-prem as well. Another question here. How can Hopsworks feature store be used in the area of Gen AI or LLM? I'm not going to talk about it too much. I have other series about it. We were talking about vector index. The vector index is built into Hopsworks. Hopsworks supports GPUs. So I have a cluster here. This particular cluster here, I have a bunch of GPUs on it. Hopsworks is used now for, you can see I've got 2 free GPUs. We use it for fine-tuning models. We also have model serving. So in this case, I was going to jump ahead about this. We have support for VLLM, which is the model serving server for large language models coming in the next release. So we're very much positioned for managing the data. And if you want to do fine-tuning and model serving on Hopsworks, that's quite widely used as well. Okay, let's slightly off topic, but let's keep going. So this was our benchmark. And if there's any more questions about it, I can take them, but we're going to move on to look at the code. The Python code in particular. No, actually we aren't. We're gonna look first at some tips for feature engineering at scale. So this is some of the things that you'll see if you want to get to this 1 million style benchmark, is that there are many different types of windows that you can use to compute features. So sliding windows is quite well known. The sliding window is, here we can see that we have a duration for our window or size. It might be, let's say it's 3 minutes long, or let's say it's 3 seconds long, and then the slide size is 2. Well, that means in Flink, because we have per event streaming in Flink, it's not like Spark streaming, which is only a micro batch architecture. When the event arrives in here, our window will compute. There are we can see 2 events in here, 2 circles. So then it will output that 2 immediately to the online feature store. Many other stream processors will not do per event streaming. They'll just, at the end of the window, so the end of our 3 seconds, they'll output the count for the window. And that means increased latency, of course. Now, there is a trade-off we'll look at in a minute, which is the size of the slide and the duration or size of your window, because obviously there's more compute needed and more there'll be more copying of data in Flink. But the sliding window is great for for having very accurate features in an AI system, because you're able to basically say the user clicked on this, how many times did they click on videos or swipe in the last 10 seconds, right? Tumbling windows are more difficult, because if we have a tumbling window, let's say of duration 10, I have 2 here, but then only at the end of the window will we output our aggregation result. It could be a count, it could be a sum, or whatever the thing you're aggregating is. So tumbling windows basically will compute some aggregation over all the events that arrive in that window, but only output at the end. So we'll have some higher latency for our features. And then session windows are also useful. Session windows, for example, if you want to have a feature which is, how active was I in the most recent session, or maybe how active was I in the most recent 5 sessions. They're pretty good indicators if you're building a model, for example, to improve engagement, and you want to predict when a user is likely to stop engaging, and then have some actions to help them engage more. Session window length, computing the length of a session is quite a useful thing to do as a feature. So they're typically computed by when events arrive, for example, per user. If there's a gap, well, then the session window closes, and then the aggregate is computed over that window, and the result is outputted. But of course, in a real-time system, because we can output this event at the end of the window, that's not great. If you can do it per event streaming, that's obviously going to be better. So this is another way to look at the same types of windows without the animation, because it's good. So let's just look at a little bit of things we've learned about the different types of windows that we have, in particular in Flink, which is a per event stream processing architecture. Firstly, for sliding event windows, they produce the freshest feature data, but they can be very computationally expensive, which I'll talk about in the next slide. Tumbling windows are less computationally expensive, and the length of your window will determine how fresh the features are. And then finally, session windows, again, are dependent on window duration. And other thing that you don't want to do is align a window to a time unit. And that might be fine when you're doing analytics, but it will lead to a loss of fidelity in your AI system, because when you're doing analytics, it might be useful to look at at events that happen over the last hour or the last day or the last week or even the last minute. But in TikTok, we care in the last seconds. So when you align along a time unit like a minute or an hour, you're going to lose a lot of your fidelity in the signal, the feature that you want to use to make predictions with. So what kind of, we have all our clickstream events arriving here, what type of features should we compute for users? Well, if I have a sliding window, I can do very simple things that can update it every couple of seconds. What was the last category of video you looked at? What was the average viewing time for the videos that you've looked at over the last 30 seconds? And they can be updated every few seconds, the sliding window. Tumbling windows might be something like video popularity. So you don't need to update them as frequency because it's not related to the user. So if it's a feature that's going to be real time about user behavior, then a sliding window is great. But if it's something that's going to change over a longer period of time, like the popularity of a video, a tumbling window is fine. It's less computationally expensive. You still probably want to do it in streaming because, if a video starts getting popular in the last minute, we would like to tell more users the next minute and then the minute after that. But we don't need to necessarily do that every hour as you would do in batch, which might be a bit slow, and then it'd be harder for videos to go viral. But if we make it too low, then maybe it'll introduce more processing overhead. And then, user historical features can be computed in session windows. So, for example, what was the most recent session time that a user had? Is there another question here? No. Okay, we're done for that. Okay, so let's have a look at the performance considerations for the sliding event time windows, which are the most important one for really real-time feedback. And this is taken from a company called Ario, who have a Rust-based streaming engine. And they show as you reduce the slide time in Flink, we can see that it's a 60-second width, so it's a window of 60 seconds duration. And they're running experiments over 3 minutes with 200,000 events per second. They vary the slide size. So if you have 5-second slide size, you can see it's still processing 100,000 events per core. So that's quite a lot. But as we reduce it down to 1 second, we're down to 25,000 events per core. So we'd need 40 cores to process 1 million events per second with a 60-second width at 200,000 events per second. What it doesn't tell you, however, is the memory pressure that this would introduce. So one of the issues with Flink is that it treats every window individually. It replicates the records to every window. So as we know, the sliding window slides across as events become available. And one example would be if you have a 10-minute window size that slides by 1 second. Well, the data can potentially be replicated 600 times. You have 600 copies of the events across all of those windows. In general, when the size of the window is greater than 10 or 100 times the slide size, the computation cost gets very high. There is a solution to this. So there are companies like Feldera who do incremental view maintenance where when events arrive, instead of having to recompute entire windows, they do incremental recomputation of the window. So if that's an issue for you, that's something I think you could look at. So the other thing I haven't defined is feature freshness. So that's the time from when the event arrives in our Kafka, computed in Flink in the pipeline, and then being available to read by our TikTok client to make predictions. So the feature pipelines, let's have a look at the code in here. This is the code from our repo. We have a backfill, so we have some historical data that we made available that you can read up. You can see here, it's actually generating that. We have a simulator to generate 25,000 events for that historical data, and we do the same for the video content. And for interactions, we're generating 1 million events. It's not a very large number, but remember, this is Python, this is not Flink. We also think it's very useful to find data validation rules when you're writing data to your feature store, because garbage in, garbage out. So there's quite a few of them here. And then we basically log into Hopsworks. We can see here, create a feature group, the table that will store all our data for the users, for the videos, for the interactions, and then we insert our data. We'll also need a feature group for ranking, storing the ranking information. And we're going to use that ranking information to train a ranking model. So that's a backfill feature. So you use it to run on historical data. It's creating the feature groups. There's a production one here, which is a very simple one, which just takes the latest data and inserts it into the feature groups. So let's move on to training. So we're collecting all of this data. We've looked quite a lot of that and how to do that at scale. Training is a background process. It's not operational, so you don't need to worry so much about the operational resourcing issues that we talked about earlier. What we want to do here is train a ranking model, and the ranking model will take data from our data model we had earlier, the interactions, the users, the videos, and it's basically going to take the ranking will have this is our labels in here. So we have the interaction ID, the event time, and so on, and we're going to compute features from, or read features from these other feature groups that we've computed already. The way it does that is that it selects the columns that you want to include as features, and it does something called an as of left join to create point-in-time correct training data. With that, we'll be able to train our ranking model. And we already discussed the training the video model and the embedding models for both the user query model and the video model. The code for those is in the repo. So let's have a look at those. Before we look at the code, let's just look at how kind of it fits together. So we have our data arriving in Kafka. We have historical data here from the data warehouse and other sources. We're putting in the feature store. We're then going to train our user and video embedding models with the two-tower model. We're going to, we talked about this already, we're going to take the model that's trained for the videos, the embedding model, we're going to read up all the videos, compute embeddings for them, and insert them in the vector index in our feature store. And then we're going to train the ranking model with the ranking data that we looked at just there. So the code for this is in the repo. Let's pull it up here. That's not it here. Okay, it's the same code. So we have, firstly, we'll look at the retrieval model and how we train that. We can see here that we're getting, firstly, what we need to do is have a feature view. So in Hopsworks, we have these feature groups. You can see these are our feature groups here: users, videos, interactions, ranking, candidate embeddings. But when we want to read data that crosses more than one feature group, we'll create feature views. So the feature view for our ranking model, we'll be able to see here, it contains features from the ranking feature group primarily. And the ranking feature group we've actually computed by pulling in data from the other feature groups. So in this case, we can see here we've got a videos feature view. Let's have a look at that one. So the videos feature view here, it has features primarily from the videos feature group. And then we have also the users feature group and the interactions feature group and the video feature group. So there's quite a lot of data coming in from other places. What we'll see here is that we want to create this particular table here. These are coming from, these are selected features from the interactions feature group, the users feature group, and the videos feature group. So the way we pull them together is we basically say, hey, I would like to have all of the interactions. These are our labels where we say the user clicked on this and they spent this amount of time viewing it, but I want to add some of the user feature groups to it. So we join on the user ID because the user had an interaction, he had a click, there's a user ID in the interactions, we join on that. We can also join on the video that the user clicked on, so it's on this video ID, and get the features from the video feature group. So we end up with the following: interaction ID, the user ID, the video ID, then the features for the user, gender and age and country, and then the features for the video, category, views, likes, and so on. This is what we call a feature view for retrieval. That's what we talk about here. That's this one here. And we see here then we have some features from interactions, from users, and videos. So that's what we're going to use to create training data. Here we're creating training data for our two-tower model. And this is the two-tower model. So I won't go into too much detail on two-tower model. We're using TensorFlow recommenders here. It's a relatively okay one out of the box. You may want to write your own one. You may prefer PyTorch. It's not a super mature area, so it's not easy to find too much beyond TensorFlow recommenders. But this is a really good example, a work-through example that we've run for quite some time. So once we have trained our two models, we're going to then write the videos to our vector index. So what we do here is we get our candidate model. This is for the videos, and we then download our videos, and then we're going to insert them into, these are our videos here, the video ID and the embeddings. So we're basically computing embeddings for all of the articles, in this case, the videos, in our system, and then we're writing them. So this is our video ID, and this is the embedding that we computed from it, and then we insert that into a feature group. So that's what's happening here. So this is the embedding. So when you insert an embedding into a feature group in Hopsworks, you create something called an embedding index, and then you add all of the embeddings that you want to add to your index here. And then this embedding object here, we just say that, oh, I'm adding this into my feature group here. So it'll basically say the column called embeddings, in this case, contains embeddings. So our feature group knows now that this particular column is a vector index, and there's going to be embeddings stored inside it. So that's it. That's basically how you write, and you populate then your vector index with that. And we now have also another feature view to get our candidate embeddings back that we'll be able to use that for. Then we need to train the ranking model. And the ranking model in this case we can see that it's going to take, again, the users, the videos, and we have this ranking feature group that we created earlier. In this case, this is going to be a super fast model, because what will happen is when we get back candidates, we may get back 100 videos. And we want to rank each of those videos with respect to the user. And we want to do it in 10, 20, 30 milliseconds. So for that, we're using a tree-based model. So a decision tree called CatBoost, which typically works with categorical features. And it's super fast. So it'll give a response in a millisecond or 2 milliseconds. So here we're training that model with the ranking data set. And validating it and storing it to Hopsworks. So the models that get stored into Hopsworks, they're available in here. You can use any model registry you want. We think Hopsworks is relatively okay. So here we've got a candidate model, query model, ranking model. And then we deploy those models if we're going to make them accessible over a network endpoint. So we've got this K-serve support in Hopsworks. You can see I'm running a couple of models, the query one and the ranking one. Typically, when a user query comes in, it can then send the user history to the query deployment model, and it will then return back with the embedding that it computes, and then you're going to pass that on to the vector index to get your candidates, and from the candidates, we're then going to go to the feature store, get back features for them, and use our ranking model then to evaluate them. So I'm not going to have a huge amount of time to go through all of the details of that. Like I said, the notebooks are available. This is the final notebook here, which is creating these deployments that I showed you. When you're deploying a model, we have support, of course, for things like get the best performing model based on the F-score metrics. So it's going to be the max one of those. And then this shows you that in K-serve, you have support also for the model itself can be what we call a predictor, but you can also have a transformer. In this case, our transformer object is doing all of that hard work. It's going to, it's going to go to the vector index, download the closest neighbors we can see here, and it's going to remove any videos that you've recently seen. Then it's going to enrich all of the IDs of all the videos that you've retrieved with their features from the feature store. And then it's going to use the ranking model to re-rank all of those videos that were returned and return them back to the user. So this, as you can imagine, is it's quite computationally expensive. And on K-serve, you can replicate this to really as many pods as you have available. So this is stateless. So when requests come in, they get load balanced by Istio across as many instances as you have. And the only thing that we can do here then is we can store the logs of all the predictions and feature values, because Hopsworks supports feature monitoring as well. So we can have monitoring support in a feature group here. I haven't enabled it here, but you can basically then monitor for drift and things like that in features. So I'm moving towards the end of the time. So, primarily, we've talked about this part already, the retrieval and ranking architecture. This is where the user query will come in. we retrieve the closest candidates from the vector index. We filter. I showed you that we can remove some videos that you've recently seen, and then we rank them using the ranking model that we've also trained, and that was the CapBoost model. So end-to-end, it kind of looks like this. User query comes in, compute the embedding, use that to find the closest candidates, enrich those candidates, or the candidates that we get back are only the IDs of the videos. We then look up the latest values for the features for it from the feature store. There could be a couple of hundred batch primary key lookups here, but that will still return in 20, 30 milliseconds. And then we re-rank them with our CapBoost ranking model. And we return the ordered candidates to the client. And this is what it kind of looks like internally. The request comes in. As I mentioned, we're using Kserve, so I do actually have a Streamlit client. We can actually have a look at that to be a little bit more practical. I think this is it here. It's running on Hugging Face. This code is available there as well. It's a very simple video recommender, but basically you can pick and say what's the user. It's just to show you kind of something working. And then it's going to generate recommendations. It's not like super fast because I haven't optimized this one for speed. But it basically then returns a bunch of videos that it thinks are recommended for you. I always think it's great to have some sort of a UI to kind of communicate the value of your models. So that's it. So in the chat, I think the link for the video is being shown. Okay. So here you can see we've got some recommendations appear here, and we can click on those to get further recommendations. So this is our Streamlit client. It's calling this over HTTPS and Istio endpoint load balances across these instances of the model being served. And then we can see we had a transformer component with a predictor, and the transformer also goes out to the vector index and the feature store to retrieve data as well. So there's quite a lot in this. If you want to take a screenshot to find a lot of the information, you'll see it here. This is the instruction for running the whole TikTok tutorial. This is the reference to the GitHub repo. This was the UI I just showed you. If you want to figure out how to configure a cluster to handle 1 million writes per second with 100,000 concurrent reads, which may seem a bit crazy because you might say, well, hang on, why is there more writes than reads? But we can see that the amount of interactions that you have to store is massive in a very scalable platform like TikTok. So every swipe, every action will need to be stored, and the recommendations then come. The reads that we do from the infra come after you go from one video to the next. So when you finish watching, it'll then look and find the recommendations for you. So in fact, writes can still outnumber reads in this case. So if you want to learn more, you can. I'd recommend this book I'm writing at the moment. The first couple of chapters are free. They talk a bit about how to build the architecture. And the one thing that I will say that's very good in the book is that it tells you how to have one architecture. We looked at it earlier, the feature, training, and inference pipelines. That allows you to build the real-time type of machine learning system we're talking about here for TikTok, but also the same architecture is used for batch AI systems and also for LLMs. So if you're doing fine-tuning, you're chunking your data in your feature pipeline, you're tokenizing in your inference and training pipelines, and you're doing RAG in your inference pipeline, it gives you the same architecture which to build all of the AI systems, which makes you much easier for teams to communicate and work together in putting AI in production. If you're interested in the performance numbers, I would recommend this particular article. This is just released at SIGMOD Industrial, and it shows that Hopsworks is by far and away the highest performance platform in this space. So we're an order of magnitude higher throughput and lower latency than GCP Vertex, Databricks, and SageMaker. And that's peer reviewed, so it's not just vendor numbers. So with that, thanks everyone for staying for the whole time. The video will become available for those of you who have registered, and looking forward to seeing you all at the next LLM Makerspace series event. Thanks and have a great day.